To today's video, and today I'll be showing you the distance between the molecules in gases. That's microfluids, one of the chapters inside the fluid dynamics or mechanical fluids. Okay, let's start. uh, we know that one is actually, I can show you the cross lines, the cross between the lines here. I'm saying that it is the distance of two molecules. Okay, we've seen that. Now if you didn't see it in water, that's in gas. In water, that distance in water, that distance was equivalent to actually 10 10 nanometers. Okay, that was in water. Now we want to see what is this distance in gases, the distance between the molecules in gases. Okay, well, to do so, we have to use the perfect gas law, which will help us to generalize our understanding in the calculations, because any gas can be fitted into the perfect gas and find the solution with slight different, but it's overall the same thing. So the perfect gas law. Okay, perfect gas, what does it say? Actually, we are saying that it occupies the total volume of the recipient. We're saying that occupies the total volume of the recipient. You see, we're saying no interaction between the molecules except by collision. Okay, we're saying there are no interactions between the molecules except by collision. Okay, collision. Actually, that collision, that's what say that is what generates kinetic energy. Okay, so to do this, we have the equation for the perfect gas, which is let's say P V equal to N R T. Okay, so that's the pressure, that's the volume. Okay, that's the number of moles, that's in this case, we'll use kb, which is the Boltzmann constant. Boltzmann constant, and that's the temperature. Okay, so then the formula, if you use here the Boltzmann constant, that formula becomes PV equal to N kBT. Okay, so for us here, we say that the oh, I want the red one. The P is the atmospheric pressure, okay, which we know is equal to 101 times 10 to the power of 5 Pascal, and the temperature, which we already know, the ambient temperature, which is 300 Kelvin, and the Boltzmann constant for us here is 138, which is well known as well, to the power of minus 23 joules per Kelvin. Okay, so now what is missing for us here is actually the volume here and the Boltzmann constant here. Okay, the volume the volume and then number of moles. That's what is missing here. And for the number of moles, we assume that for 1 meter cubic of volume, we're assuming that we'll say that the number of moles per each meter cubic should be equal to the pressure over the Boltzmann constants and the temperature. And then this gives us 101 times 10 over 5 Pascal over 138 with Boltzmann's constant times 10 to the power of minus 23 joules Kelvin times 300 Kelvin of the temperature. This gives us approximately 244 times 10 25 to the power of 25 moles per each meter cubic. It means that per each meter cubic where the gas is, we have approximately 2.44 times 10 to the power of 25 moles. Okay, that's what it means. We have 1 meter cubic of volume. Inside it, we'll have actually this number of mole. That's what that number means for us. Okay, and if you go back to the formula here, we'll find out the volume should be equal to you say the volume, well, that's the formula here, should be equal to N kb T over the pressure, and then that will actually if we do the calculation, gives us approximately 1 times 10 to the power of minus 26 meters cubic. Okay, and again we'll use the same. We know that volume actually is a multiplication of three parameters. The larger the depth, the distance, the larger, and the complement of a certain recipient. And from this we mean that we have something, call it let's say x to the power of 3. That's the volume, and then that x should be equal square of that volume. Okay, and x should be equal to times 10 minus 26, that's meters cubic, and our x here, the distance, should be equal to approximately 344 nanometers. Okay, that's the distance in gases. Okay, in gases. Okay, and we've seen that the distance in, let's say, in liquids is approximately, in liquids we find the x equal to 310 nanometers. So that shows us something, that the distance in gases are much higher than the distance in liquids. Okay, so thank you, and that's it.